Hey guys, welcome back. So today in this lesson here, we're going to be talking about inductors, self-inductance, and inductive reactance. And self-inductance an inductor in general is a coil. Okay, anytime you have a coil, it is going to be an inductor, and it will have self-inductance and it will have inductive reactance if you connect it to an AC circuit. It's just a fact of life, and so we got to figure out what it is and how it works. And then we're going to look to see how it works in AC as well. But for right now, I want to actually see how this thing behaves in DC, because it's a little bit easier to understand how it behaves in AC if I understand how it works in DC. And so I've drawn a little coil here, just a winding around a metal core of some sort. I got a DC battery here, and I got a switch, and I can open and close the switch and make things happen. Now, I've also, sliced this in half and drawn a, image of the cross section of these conductors, because what we're going to do is apply a bunch of the right-hand rules that we learned in level 2 to the magnetic fields that are around these conductors in order to determine, how the magnetic field from one conductor affects the conductors that are adjacent to it in the coil. Okay, guys? So if I close this switch and current started to flow, the first thing I've got to draw for you here is the direction that the current's actually flowing in these conductors. And if you recall from level 2, I can draw actually a cross or a dot in these conductors based on whether the current's flowing into the page or out of the page. And if you remember, if you think about it as an arrow, you are either actually looking at the point of the arrow, in which case you would see current, you would see a dot here, and that would mean that current's flowing towards you. The other thing you could see is a cross on here. And if you see a cross here, that means that you're seeing the feathers, and so that current is going into the page. And so in this particular case, since we're doing conventional current flow, current would be flowing up here into the page on the top and out of the page on the bottom, which is why I drew, a cross in the top here and a dot in the bottom. And in fact, all these guys on the top here would be crosses, and all these guys on the bottom will be dots. Okay, guys? So now if I took a look at this here, if I close this switch, guys, and current starts to flow, a magnetic field will start to appear around these conductors. And not only does it appear around these conductors, but it actually blows out from the conductor. And as it blows out from this conductor, that magnetic flux will actually cross the conductor next to it. And as it blows out from this conductor, that magnetic field will actually cross these two conductors that are next to it. And anytime you have a conductor moving through a magnetic field, you will have a voltage induced into that conductor. And so even though nothing is physically moving here, the magnetic field from one conductor is blowing out and therefore moving, relatively speaking, past the conductors that are adjacent to it. In order to figure out how the magnetic field from this conductor will affect the conductor next to it, I have to apply a bunch of right-hand rules. There were, a couple of them. We learned them in level 2. Don't worry about it. I'm not going to test you on it. I'm going to demonstrate it here for you so that you see it. And, we won't worry about it too much after that, okay? So if I want to figure out the direction of the magnetic field around this conductor, well, I have to apply this right-hand rule right here, where my thumb is pointing in the direction of current flow and my fingers will point in the direction of magnetic field. Okay, guys? So I'm going to go thumb into the page. Since the current's flowing into the page, magnetic field looks like it's clockwise, and so you would get this magnetic field that looks like this around there. And it would actually be blowing out like that and crossing this conductor. Now, if I want to figure out the voltage that's induced into this conductor, I can do that with another right-hand rule. It would be this rule right here, where your thumb represents the direction of current flow, your first finger represents the direction of the flux, and your center finger will represent the direction of the induced current or voltage, okay? And so if I wanted to apply it to this conductor, well, this red flux is moving out past that conductor in this direction, so the motion of this conductor relative to the field is actually in this direction, so that would be the first finger I have to figure out is the thrust is this way. The second finger is the direction of field, looks like it's down. So I got thrust this way, field this way. This finger here is going to point in the direction of induced voltage, and look, it's out of the page, which means I've got two voltages occurring right now. I've got the voltage that's applied because this battery, and I just closed the switch. The second one is the voltage that's induced, which is actually the opposite direction or out of the page. And I don't care, guys, which conductor I pick. If I apply those right-hand rules to any one of these conductors, I will always find that the moment I close this switch, the magnetic field that's expanding around the conductors will always induce a voltage that opposes the applied voltage in every single adjacent conductor. Okay, guys? And so if I want to see what that looks like over time, I've got a little drawing here that we're going to look at. And the first thing we're going to do is draw the voltage, guys. And it is going to be this green line right here. And if this switch is open, guys, then there is going to be no voltage. And there is also going to be no current. Where's my blue marker? Here it is right here. So this green line is going to be voltage. This blue line is going to be current, guys. And right here, I'm going to close the switch, okay? And the moment I close the switch, guys, my voltage is going to go boom, right up to, you know, the applied voltage, whatever voltage that is, E applied, okay, guys? And at that instant, the current's going to want to start to flow. The magnetic field is going to expand out. It's going to start inducing voltages into the adjacent conductors. And that induced voltage is going to oppose the applied voltage. And so even though I've applied a voltage this way, I'm going to have an induced voltage this way. And the current, because the voltage is being opposed, the current is going to remain zero. But this magnetic field eventually is going to stop expanding out. It's going to expand out a certain amount and then stop. And so the induced voltage, even though it's going to be high at the beginning, it's going to be reduced by the fact that the magnetic field eventually stops. Okay, so you have an applied voltage that looks like this, and you have an induced voltage that looks like this. And what you get is a current that looks like this. Okay, it takes a second to get going. Now, you know, there's this period of time here, guys, where, you know, Ohm's law is not applying. But eventually, the current comes up to the Ohm's law value and will continue to flow at the Ohm's law value, you know, until such time as I make a change to the circuit. Now, right here, guys, I'm going to open that switch, okay? And if I open that switch, well, the applied voltage is going to drop right to zero. And by the way, guys, this right here, blue line here, is going to be the current. All right, guys? Now, if I open that switch, the applied voltage is going to go down. Now, as soon as the applied voltage goes down, this magnetic field is going to slam back down. And if the magnetic field from this conductor slams back down towards it, it's once again going to cross the conductor that's adjacent to it. And if I apply all my right-hand rules, guys, I'm going to find out that the voltage induced into this conductor, because that magnetic field is crossing it, is going to be in the same direction as the applied. And so once again, I get an induced voltage here, guys, and it is, in this case, in the same direction as the applied. So even though I've turned the applied voltage off, I get an induced voltage spike here again, which trails away like this as that magnetic field collapses and stops collapsing. And what that causes is the current will tend to want to continue to flow, okay guys? So it'll flow like this and then eventually be zero. And so what does this all mean? What it means is with a coil, when things are changing, you get a current that doesn't seem to apply. It takes a little second to get going here, and it takes a little second to stop here. This device here is storing some energy, at the beginning when I first turn the circuit on, and then it's releasing that energy, when I turn the circuit off. All right, guys? So come back for the next video. All right, guys?